Okay, so let's just use this high Reynolds situation that we were talking about before. Instead of the low Reynolds where it was in glycerin tanks, let's study the high Reynolds. Because high Reynolds is usually air flowing over foils, and that's what you care more about than a little marble dropping in some glycerin. So, right, you came up, experimentally, you can come up with this. You have proportionality drag proportional to speed squared density and the size squared, right? What does that mean, right? So if we read an equation over there, we could say I have the drag force and for usually keep this here just to make everything look nice. And so just putting variables to what this is saying. Anyway, this is an area, and it's the frontal area, or right, the area. So if this is, so frontal area being if this was a ball sitting in a sphere, right? This frontal area would be right pi, right, be pi r squared. It's projected area on right frontal area. Well, it's just a size squared. Usually for this, right, you can even estimate this by just having your largest distance of your thing squared, and it can give you even a pretty good idea. So that's the thing of really this whole coming thing in terms of Darcy friction factors. Now we're looking for this number, and it's good, right? And that's the whole point of the analysis then, is I'm always looking to calculate this drag force. I want to get at it. I know my velocities usually. I know the density of the air I'm always looking for. But for an area frontal, you design that all the time. So it's really a question of what in the heck is this coefficient of drag? Just like those movie things, that's what we're going to get at, right? And it makes it just so easy to calculate drag force if you can get this value. So you can get it through the experiments, which is what you could do. You know, a lot of people actually do them. You kind of do all of these things. You do it numerically, you do it analytically, and then you do it experimentally. No one's making an airplane and not measuring to make sure they have that number right. But that is just sort of the key feature about what we need to do, and that's get this value so that you can calculate a drag force pretty quickly. And then we'll see here that this drag is mainly a function of that Reynolds number. So just as in with these Darcy friction factors, you calculate a Reynolds number and you wouldn't believe the things you can calculate past that. Check the notes. I have a nice extra credit that's kind of fun for that for all these relationships of low Reynolds and high Reynolds, the drag force relationship. You can get that from the arguments of the Navier-Stokes. So give that a try, and it's kind of fun how you can just derive this just from the Navier-Stokes equation. You can derive this relationship. I'll give you a little hint in there, but I would give it a go. So where does this coefficient of drag arise, and where does it come from? So I'll explain that. Oh, it's only. So where are the subtleties, or where's the complications coming trying to come up with this drag coefficient? So we need some fundamental truths that we have to hold on to if we're going to go ahead in this analysis. And I want to say the biggest one that's going to motivate any of our analysis is this idea that the no slip of the wall is very fundamental to any fluids, right? And you can verify this in an experiment even. If you have a tank of, let's say, a thick liquid like a glycerin, then a dyed, and then some dye here, right? And say you just place some strip of glycerin right there. So this is all really thick liquid. And this is a false bottom that you then pull out. So this is, I've deposited a sort of a thick worm of thick glycerin that has a dye. I can visualize it and see it. And it's sitting in a tank of also thick glycerin, but of a different density. So this is a line of dyed glycerin, right? So then there's a line right here. If you pull this board, you will very distinctly see this. You'll see this glycerin shape sort of stretch out like this. But notice that even in this experiment, right, this it doesn't move, right? So you experimentally can just visually see the fact that this no slip condition always holds, right? It's just what you did in the pipe flow, right? Right? The velocity at the wall is equal to 0. There's no slip at the surface or no relative slip. So that's the biggest thing you have to hold on to if you're going to look at these external flows. External meaning if I do have some airfoil shaped thing and it's sitting in really fast moving flow field at a U, right? U infinity is what you usually denote it. Here's my airfoil shape that's sitting in this very fast fluid, right? It's so fast that it's mostly inviscid, so the viscous forces and inviscid, they much dominate. It's all inertial, it's all these inertial forces happening. You get these streamlines that go around, and that's what we usually plot for something like this, right? And the effect is like that. If I just zoom right at any point in here, these still look parallel. Parallel means inviscid. Same thing down here. These still look parallel. Parallel meaning inviscid. But, right, I just told you that that no slip thing has to be true. So this whole idea is, if I were to zoom in really, 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 really close to the surface of this thing, right, I would, right, there has to be a point, even though this is going really, really fast. It's very fast moving fluid. It's an airplane, for Christ's sake. If you get down to here, I still know, let's say if I measure my coordinates right here as y, I still know the velocity at 0 has to be 0. It has to have no slip. So that's the concept of what a boundary layer is. If I zoom in onto this airfoil really, really, really closely, right? So let's take this image. So after this axis right here, I'm zooming in right to the very front of the surface. And it looks like this. I have drawn this picture so many times. But you gotta do it. Where, sort of past here, it's all parallel inviscid flow. There is some distance here where it has to go from being 0 to, after some distance, it then reaches this and it's just constant throughout. This is what we call the boundary layer. Right? The boundary layer is some distance that it has to reach to go from this mostly inviscid flow, because it's going so gosh darn fast, to this viscous part. So you'll see these things right here where this is sort of viscous flow. Viscous flow, if the dimension of y is below delta, and then above it you have inviscid flow. Remember, the inviscid flow is just a Navier-Stokes equation. It doesn't have that viscous term. It doesn't really matter. But even if you had high Reynolds, even if all of your fluid is really high Reynolds number, this constant boundary layer is saying, well, if I zoom in close enough, I know there has to be some point for the viscous forces to matter, because I really believe in the no slip a lot. And that distance is what we call the boundary layer.